Welcome to Altair Engineering Training and Support. I am Apurva Bhatt and welcome you all in dynamic crash analysis of roll cage for BAJA SUPRA, FSAE Mini BAJA, BSI, FSAE. In this series, I am going to use Radios, Hypermesh, Hyperview, in which I am going to show you the different versions of like version 11, 12 and 13. So till date, the topics which I am going to cover in this complete series is 2D meshing and quality check of dynamic analysis that I have covered. So today I am going to show you how to create a deck, a solver deck for front impact dynamic analysis of roll cage using Altair HyperWorks version 12 and 13 when we have pipes of different thicknesses. So here we are going to use Hypermesh to create a deck and Radios to solve the dynamic analysis. Then we will use Hyperview and Hypergraph to view the animation and graph plots. Then in this way we'll start. Next days will be like the topics which I am going to cover in day 3 is side impact, rear impact, front impact. Then it will be front impact, side, rear in version 11. Then front, side, rear in version 12 of the same thickness pipes. Then front, side and rear impact between the two vehicles, head-on collision. So we'll complete the training series in 13 days. So we are into day 2 where I will show you how to create a deck for front impact dynamic analysis of roll cage. So in last video we ended up with the meshing, material and properties and updated the component and save the file. So I will again save the file. So I'll go to file, save as, create a folder and save this file. So I have saved a file in the folder. Make sure to save the file in any other drives other than the Windows drive, so or not on the desktop, because it will a solver will create X number of files on that particular folder. Also make a folder and save the file in that folder. So whatever file it will create during the solution, you will have all the files in one folder. So don't run the file in open space or open drive. Make a folder and save the file in that folder. So you can see I have saved the file in D drive in a new folder. So now whatever I'll solve, it will come in the new folder 3. So the next step after creating the material properties, meshing, editing the mesh as per the qualities required for the dynamic analysis. So we will start with the solver creation deck. So the first point to start with creating the deck for front impact dynamic analysis is to create contact. So to create contacts, I'll go to analysis, interface, enter the name as interface, whatever name I want. I can enter contact. We'll use type 7 as the contact, card image as type 7. You can define any color of the interface contact that will come here and click on create. So you can see a group of contact is being created. Now I will go to add. In master I will select components. In slave I will select components. So now in master I will click on comps, select both the components and click on update. Make sure you click update whenever you select a component. Then in the slave I will click on comps, select both the components and click on select. Again I will click on update. So I have to click update twice. First selecting the components in master, both the components, click update. Then select both the components in slave and click update. Then click on review to see the contacts. So the contact has to be like this only, the red and blue. Red will show you the master and blue is the slave. So I have both as master and slave. So this will help me to define the contact between the elements. Now I will go to card image and click on edit. So first thing you have to see here is, so the interface of master has 2 components and slave has 2 components. So I will scroll down So then the first parameter which I have to define in this is ISTF, which defines the stiffness, the contact stiffness should be calculated. So this I will enter as 4. Then gap minimum, which I will enter as 1, and INACTI, which will tell or help us to calculate the penetration treatment of the nodes, which I will enter as 6. Then I will click return. So the parameters which I am entering here is explained in my dynamic analysis series. So you can go through that videos. So you will get a brief introduction of these parameters, what are they. I am not explaining here because the length of the video will increase. So as it has already been explained, so I am skipping the points of explanation. Again I will click return. So my contact has been defined. Now the next step is to apply the loads. So for dynamic analysis in version 12 and 13, to apply the loads, we'll go to utility tab. At the top you can see, go to BC manager in tools, enter the name. I will enter as velocity. Select the type as initial velocity, put initial velocity, nodes all, proceed. Yeah. So as you can see, I have entered velocity, initial velocity, GR nodes all, proceed, and enter the velocity. So Vx, Vy, Vz. So in which direction you want the velocity, you will enter here. So if your roll cage is in -x, let's assume. So if you put like this, and if the direction is, you can see the x direction is in this side, so you have to enter minus velocity here. So it will be in this direction. So this minus or plus will represent the direction. As you can see is in positive direction, so I will enter here positive value. So here we'll enter the velocity as millimeters per second, because all the parameters I am using as tons, millimeters, seconds and Newton. So let's assume I want to analyze this model at a speed of 60 km per hour. So if I want to analyze this model at 60 km per hour, so I will convert that in millimeter per second. So 60 multiplied by 5 divided by 18 will give me meter per second, and 1 meter is equals to 1000 mm. So I will multiply with this 1000. So my velocity is 16,666.66 millimeters per second. So now I will enter this here. We'll keep other parameters as it is and click on create. So this will create my boundary condition. So I will review this. The direction has to be proper in this direction. So you can see my velocity is in this direction. So you have to review it before going further. Just review the direction of the force. So click on clear review and close it. So now I have defined the interface, applied the velocity. Now I will create the rigid wall, which is the next step in dynamic crash analysis. So to create the rigid wall, I will go to analysis page. On analysis page, I will click on rigid walls, which is on 4th column, 2nd row. Enter the name as front wall. I will create 2 walls, one at the front, one at the bottom. The type is R wall. This size doesn't mean the size of the rigid wall. If you put 1, we'll create an infinite plate, a rigid wall. So that doesn't mean if you put 10, it is just the representation. So if it's 10, it is smaller. If it's 100, it's bigger, but that doesn't mean that it will not impact properly. So we are creating the complete infinite plate. So I will click on create, then I will go to the next step, that is geometry. Select the radio button as geometry. Select the base node at the front. I will select this. Go to edit. So I want this node to be some distance away from the roll cage. So it will travel some distance, then impact and then bounce back. So I want this node in this X direction away. So I will increase the length 1420 and click on return. So you can see I am creating a rigid wall 10 mm away from the roll cage. You can create a rigid wall whatever distance you want away from the roll cage, and select the normal vector. So the normal vector has to be in opposite direction of the roll cage of the velocity. So you can see here, if I pick X, so it will take positive X axis, so which will be on the same direction, so the impact will not happen. So I have to select N1, N2 and define with the direction. So I will pick any straight line for N1, N2. Even I can pick this also. So this one as N1, and just the front of it as N2 and click on update. So you can see I have created a rigid wall. This is of 10 by 10 and you can see the direction here. This is most important thing. So if this direction is an opposite, then the contact will not happen. So the impact will not happen. It has to be in opposite direction of the force, or sorry, velocity. Then go to add, select the nodes, all, and deselect this node of wall and click on add. Now you have to review this. So it has to be blue where the impact will happen, and the nodes which are going to impact are red. So that are the things which I have to add to create the wall. I will click return. Similarly, I will create one more rigid wall for the bottom. I will turn off this. So I will create one more wall for bottom. R wall, create, geometry. So deselect the initial node, this one, and we'll create one more node here at the bottom, edit. So this time I want the node to be in Z direction but minus Z direction. So I will increase like minus 346 and return. Again I can pick the direction as Z because Z is in positive direction. So I will click update. So we can see the direction is set. If it's in negative direction, then only we have to pick N1, N2. If the direction is in positive, so I will pick directly the axis here. Now add nodes all. We will deselect this one. Also we will deselect this one. So make sure to deselect the node of the wall and click on add and review. So you can see all the nodes are in contact with this wall. Then I will click return. So my wall definition is done. Now the next step is to create the output request. So I have two components. That's why I will create the output block. Enter the name as output. Select components. Select both the components. Click on create. Then edit. enter the variable name as def, so default. So whatever now we will get three outputs, one for this component, one for this component, and one for combine. So if I want to see the deformation stress values for a particular component, I can see that also, and I can see the combine also. So that's why I requested an output request for all these things, and I will click return. Again I will click return. So now the next step, or the last step before solving the radius dynamic analysis of the crash analysis of the roll cage, is to define the control cards. So for the engine file, like in dynamic analysis, it creates two files, the run and the engine. So to define the engine file, we have to define four important cards. If you don't define those cards, your animation will not run, or your model will not solve. So the four cards which you have to define properly are as follows. First, click on analysis control cards, go to next. The first card is engine run. Enter the value as t-stop. Here t-stop means for how much time you want to solve your model, how much time you want the solver to run to get the results. So how you can decide it? We'll decide it like, we have the velocity as 16,666 millimeters per second. So it will be like 16,666 millimeters per second. So in 1 second it will travel 16,666 millimeter. So that means it will take for 1 millimeter travel, it will take 1 divided by 16,666 millisecond. So I will open the calculator again. So for 1 millimeter travel, it is going to take this much of time. So this is from 0 to 10 millimeter and bounce back. So it will travel 20 millimeter, but for a safer side, I am calculating 40 millimeter solution. So I will multiply this with 40. So this is my runtime, that is 0.002 seconds. So I will enter here as 0.002 seconds as the t-stop. Then I will request for engine file. Engine animation dt, one more card. Here t start means the animation files, it creates different animation files, the result file. So by what time you want to start the animation file? So I want to start it from the beginning, so 0. And t frequency means after how much interval you want the animation file to generate. So in general practices, whatever time you give as a t stop divided by 1000 is the t frequency. So I will divide this with 1000. So this is my animation frequency, which is 0.00002 is my time frequency. Now the next card, which is important to solve the model, is engine T file. So I will next, it's all alphabetically, so you can go accordingly. So engine T file, here the time frequency is the points which it will generate to represent the graph. So if you put it very less, the graph is very sharp. If you put very high, the graph is smooth. So I want a smooth graph. So this in general is taken as whatever the t-stop value is divided by 10,000. So I will enter here as 0.0000002. as the time frequency. Now the last card is engine animation element. This will help me to give output results. So I want, by default it will calculate the displacement, so I want plastic strain also, von Mises stress also, and hourglass energy also. And one optional card is there, that is engine ABCD. Engine mon. So I will put mon on, so it will tell me the estimated time to solve this model. So I will click return. This is optional. If you give, it's okay. If you don't give, still it's okay. So now my deck is properly completed. Now I will again save this file. Go to analysis, radius, export option to all, run option to analysis, run number 1. Here in options I will put dash both space dash n thread space 4. Both means it has to run both the files. It has to take both the files for solver. N thread means number of cores. So dynamic analysis radius will not take your RAM, it will take the cores. So I am giving here the maximum cores which I have in my laptop. So you can put, if you have 8 you can put here 8, if you have 2 you can put 2. So generally by default it take 1. So what you have to put here, the n thread space whatever the number of cores you want, and click on radius. This will start the solver. So you can see here it has started the solver process. Generally it takes around 3 to 4 hours to get the results. You can see here it has started writing the animation files. Hyperview will take only 999 animation files. If it's more than that, so it will not take more than that. So you have to decrease your time frequency, T frequency value, which will be on the engine NMDT card. So earlier I have put on a higher value. So if the animation file after the solution is high, so you have to decrease it to 1/10 so that the animation values will decrease and you can capture the complete animation. So you can see here my animation is going on and on, so it will definitely cross 999 value. So I don't want these much values of the animation. So I will stop and kill, close. So apart from HM file, so what I will do, again I will save the file in new folder, save, and just change the value of engine NMDT to 0.00002. I have reduced it to the 10th time. So I will save this file again and run the animation. So I'll you can see it as starting the solver. It will check the deck first and it will start the solver. You can see here. So I can see here, you can see the frequencies of animation file is quite lesser this time. So it depends on you how much file you want. If it's generating more than 999 files, so you have to stop the run and decrease the time frequency in engine NMDT card and again solve the model. So this time frequency and T frequency card will not affect the solver, but it will affect the memory, because you can see the each file it will create is of 2.7 MB. So it will unnecessarily put load on your memory. So you can increase or decrease this value as you want. So it will take some time, approximately 3 to 4 hours to solve. So once it's solved, I will tell you how to see the results and graphs. Okay, so you can see as it has solved. So I will click on, instead of clicking on result, I will click close, go to start, all programs, scroll down to HyperWorks Altair, Hyperview. It will take another some time to start. You can see on new folder, it has generated 101 files. So if earlier I have 10 times more number of files, so it might generate 1001. So I have reduced it to 10, so it has generated 101. So you can put odd numbers also. So you can divide it by, instead of 10 divided by 5, so you will get somewhere around 500 animation files. So as you can see, my animation is here. So I'll split the window, because in dynamic analysis we see graphs also. So I'll split the window, in one hyperview, the other one is hypergraph. Sometimes you will find a black screen instead of this graph. This is because of your driver updates. So you have to update your drivers. Once you update the driver, you will get this window. So you can check with your laptop vendor to update the proper display drivers. So I will open the file, my computer, 4th, the animation file 1, roll cage A001, 2, I will direct it to the last file A101. T01 is the graph file, so don't open this. You have to open A files, A101 or 001. These are the files for animation. Open and apply. So this is my animation. This is the hyperview. And here I will apply open the graph. So on new folder, I will open T01 file. Select global variables. Select global variables, internal energy, kinetic energy and total energy. This is the most important graph which I have to check during the impact analysis. So now I will play the animation. So I will see the displacement. So you can see the total energy remains the same, kinetic energy is decreasing, internal energy is increasing as the impact goes on. So if you are not able to capture the bounce back effect properly, increase that T-stop value. So increasing that T-stop value will help you to capture the bounce back effect. So here the impact happened. The displacement is coming as, you can see it's continuously increasing the displacement as the time is going on. So I will see von Mises stresses also. So these are my von Mises stresses. So here it should cross these 2 points and then again go back. So because of the lesser time frequency, the bouncing back effect is not captured properly. So I have to capture that bouncing back effect. So we have to increase the time frequency graph. The t-stop value I have to increase it. Earlier I have given 0.002. So now I can give 0.008 or 9, something like that. At least earlier I have given 0.02 seconds, so I want to increase it. So I have given 40 milliseconds, so that I have to increase it to 100 milliseconds or 120 milliseconds. So that you have to increase, which I will show you here. Control cards. Next, in engine run, this value. So increase this value to, this means 20 milliseconds. So I have to increase it to somewhat more, like 40 or 50 milliseconds, or sorry, 100 and 120 milliseconds. So in this way you can do the dynamic crash analysis of your roll cage. So thank you very much for watching the video of day 2. In this way I have ended with the day 2, dynamic crash analysis of roll cage, front impact crash analysis of roll cage. If you have any queries or issues, feel free to contact us at apoor.bapat@altair.com or edu-support@india.altair.com. Thank you for watching this video.